For those of you who have just walked in, I am Karan, Ahuja, a PhD at Carnegie Mellon University. I'm going to be presenting my work on MeCap, a whole-body digitized approach for low-cost AR/VR headsets. This work has been done in collaboration with our session chair, Robert Xiao, Chris Harrison, and my advisor, Mayank Goel. Okay, so low-cost virtual reality headsets powered by a user's smartphone have become increasingly popular since the introduction of the Google Cardboard in 2014. Since then, we have come a long way. There have been a proliferation of multiple emergent designs, such as the Google Daydream and the Samsung Gear VR. While these smartphones provide powerful compute and sensing capabilities, the interactive VR experience is typically limited to physical controllers. More expensive headsets, such as the Oculus Rift or the HTC Vive, often bundle wireless, battery-powered handheld controllers to boost interactive expressivity. These enable tracking of the hand position and provide physical buttons for basic grips and action. However, no consumer headset today out there provides full body, hands, and mouth, aspects that are clearly important in immersive virtual experiences for full-body gaming to social avatars. What we ideally want is a sensing mechanism that instruments a single point on the user and can see their full body, hands, face, and physical appearance, along with contextualizing their immediate environment. So we are not the first to think about this. The academic research community has been looking at various parts of these. In terms of optical tracking, there exist very accurate motion capture systems such as Vicon and OptiTrack. Another approach is using almost commodity cameras. So the implementations that fall into this category include the Microsoft Kinect, which makes use of depth cameras, or also approaches that make use of RGB cameras such as OpenPose and VNect. There are also other non-visual sensing approaches that make use of RF reflections or capacitive sensing. In terms of worn motion capture, Shitori et al. Instrumented the body with 16 wide-angle cameras to get the pose of a person. There also exist body suits, such as those by Xsense, which use IMUs on the body to track the full body pose. In terms of worn sensing, our literature is more common with those in extended reality systems. Here, researchers have looked to instrument the headset with more sensors, as can be seen in the paper by Howley et al., in which they point an RGBD camera sensor to capture facial expression. Another paper is EgoCap, which makes use of 2 additional cameras cantilevered off a helmet to capture the user's body pose. So MeCap does all this and more, without the cost of any extra sensors or external infrastructure, and is entirely worn and self-contained. So MeCap provides 3D body skeleton, 3D hand skeleton and gesture classification, mouth classification, apparel, and skin sensing. We achieve this by using a smartphone's rear-facing camera and using 2 mirrored hemispheres, which are placed roughly 15 centimeters in front of the headset. So, as you saw the previous design, we also envision a more commercial design that uses macro or wide-angle camera attachments. So at the inception of this project, when I first started, I used sort of this hemi-spherical spheres to get this fisheye view of the whole body. But now there are sensors such as the Oculus Rift S, which have 4 cameras that pretty much provide you the whole body skeleton as well, the whole body view as well, which has this sort of distorted view similar to that of MeCap. So what we assume is the same algorithms can be used to extend this and to use on these devices and this design form factor as well. So keeping that in mind, let's go over what MeCap provides. So MeCap provides using this headset, we will now see the view that this provides. The MeCap accessory offers a distorted but complete view of the wearer through these hemispheres. So we unwarp this view to get a better representation of the view of the user in this environment. We can then take advantage of existing state-of-the-art algorithms to extract pose information, as you can see in the video. A single labeled keypoint image does not provide us with any depth data. Therefore, we use the views from both the unwarped spheres and do stereo correspondence on top of the pose data to extract the missing z-axis data. We also capture the mouth, which we can classify into neutral, smiling, frowning, kissy face, and mouth open. We can also extract patches from the video to estimate skin tone and apparel. This rich data can be used in many end-user applications. Currently, when the user has to make social avatars, the user has to customize their skin tone, apparel, alongside with other attributes in a very manual process. MeCap can enable automatic personalized social avatars, as you can see with my amazing stick figure over here, conveying not only body language and gestures, but also apparel. So another great thing with MeCap another thing that is needed in augmented reality is lighting. So currently techniques exist, for example, the Apple's AR kit can make use of the lighting and a global lighting scheme to give you a directional light for a virtual object or mixed reality object that you place into the room. However, there is no automatic way to capture the environment map with multiple illumination sources. MeCap can use the processed camera data to generate this environment map to enable realistic object lighting and even reflective objects in augmented reality, as you can see. Currently, in virtual reality also, whenever a user has to sort of choose a tool, it requires pointing and targeting this oriented selection of a tool. For example, if I want to use a brush in virtual reality, I'll put on my Google Daydream, select the brush, and then I will just choose it, which is very unnatural in nature. So MeCap's hand tracking can also unlock expressive input without the need for any gloves or controllers. Here you can see the controllerless hand input using gesture recognition to summon different virtual objects. So now I will walk over the various studies we conducted to test the efficacy of MeCap. To evaluate our 3D spatial accuracy, we set up two checkerboard patterns perpendicular to one another with the camera above. From the controlled viewpoint, the 3D coordinates of all the intersections of the checkerboard are known in real-world physical units. We then manually annotated all the intersections and had MeCap compute the estimated 3D positions, which we later compare to the actual position. We can see, so over here you can see the 3D spatial accuracy. We achieve a mean 3D Euclidean error of 2.3 centimeters, roughly. And you can see as you move away from the optical axis, the error increases. We also estimate the pose estimation of MeCap. We asked 10 participants to perform 8 different body poses and manually annotated key points for ground truth for comparison. We found that we could see 96.9% of the key points in all the frames. So that means of all the total frames we captured, in almost 97% of the time we were able to estimate the pose of the person. In the remainder of the cases, due to bad unwarping, the information was lost or other cases. We also saw that the mean normalized error was 0.3. This is the mean normalized error with respect to a shoulder width. So if the mean normalized error was 0.2, this means that the key points were misaligned to roughly 1/5 of the shoulder width of a person. We also tested MeCap as a discrete hand gesture classifier as well. So for this, we collected 5 one-handed and 5 two-handed gesture sets. For the one-handed gestures, we used open hand, gun, the OK gesture, Spider-Man, and closed hand. For our two-handed gesture set, we used ball, holding a book, hand holding together, hand in a prayer, and wheel. We found that our accuracy across both these gesture sets were roughly comparable, and we had a cross-session accuracy of 96% and a cross-user accuracy of almost 80%. For the mouth state recognition, we asked 10 participants to perform 5 mouth states. We collected the data across 3 sessions. Our mean accuracy was 95% across sessions and 65% across users. So we know, upon analyzing the data, we found that our cross-user accuracy was quite low due to the fact that different people perform different facial expressions in different manners. So for example, if you ask the same person to smile or frown, different people to smile or frown, their facial expression will be quite different, hence it does not generalize quite well across users. So for skin tone and apparel tracking, what we did was, for skin tracking in particular, we asked the user to pick their skin color from a Fitzpatrick scale. So the Fitzpatrick scale is a scale of skin tone that goes from light to dark on a scale of 1 to 7. So once a user picked sort of their own skin tone, our system then predicted a skin color patch for them as well. And then they sort of they told us whether that patch was correct or not. And in the case it was incorrect, by how much off was it, we recorded that. We found that our skin color recognition accuracy was 90%. And in the case it was off by at most only 2 skin patches out of 7. So for shirt color and pant color, we use a similar scale out of 10, and we found that the skin color for shirt we had an accuracy of 7.1 out of 10, and for pants it was 7 out of 10. So let's quickly. So while we present MeCap, there are still some ways to go before we can use this in our everyday lives as a single point sensing information to enhance our experiences in virtual and augmented reality. First, we need a better industrial design. And also, we need to overcome the latency constraints of pose machines and unwarping. So currently, we have 2 implementations. One is slow on the phone due to the compute time it takes to estimate the pose of a person. And the other, we have a cloud version in which we transmit the data back to a server and get the annotated data back, which is slow due to the latency. And also, the rear camera view is obstructed when we use this approach in virtual reality, and hence, we cannot use it we cannot see from the rear-facing camera towards the outside world. Thank you, and I will now take questions.
All right, thanks. We have time for a number of questions, so please do ask questions. And also, just for people who are leaving the room now, just do keep in mind that you should vote. I'll remind you to do that before the session ends. Question back there.
Are you using any machine learning for recognition or hand gesture recognition?
For machine...
I mean the machine learning.
For hand gesture?
Yes.
Okay. So
because you can also achieve human level accuracy.
You can achieve what? I'm sorry.
You can also achieve very high accuracy using machine learning. So are you using in your system or not?
That's a good question. So yes, we are using machine learning algorithms for the hand gesture classification. What we do is we make use of the pose key points and then also extract a patch of the user's hand that we feed forward into a VGG16 convolutional neural network, out of which we take these features, concatenate them, and then learn based on them.
So I actually had a quick question. In the actual spheres that you use, they're not always completely flat. And so can you speak about basically if there's imperfections in the actual spheres, how that might affect your tracking?
So if there are any imperfections within the sphere, we do note that our accuracy for 3D spatial accuracy for the key point estimation does drop. So yes, ideally we would want them to be completely spherical or nearly spherical in nature. Otherwise, the 3D stereo correspondence fails due to mismatch in the physical coordinate space. So that is, yes, you can calibrate that out if you pre-know what those are and if you do attach a calibration phase to it before using it.
Okay. Sorry to...
No worries, sorry. I hesitated. Hi. So you gear this towards the low-cost VR stuff. The low-cost VR systems are kind of being swept away. Do you see part of your algorithms and research be applied to like when you actually have a fisheye looking down or something like that on the more high cost?
Definitely. So once we have this, so the key idea, so we used this attachment to get sort of that view that these cameras, like the Rift S now provides, as I showed in my slides. So if you have these 4 cameras, you can now get a full view of the user and also hands when you extend it and put it behind the head as well. So definitely you can use those systems as well now, and hopefully the algorithms will run the same way because it's almost the same image type, basically.
Okay, thank you very much. Let's thank our